Okay, question 5 is about the shape of magnetic fields. So we can see it's already done our butterfly straight curve for us. So we're pretty happy with that. And it says draw arrows to show the direction. So it's just testing us, do we know that they move north to south? So draw arrows north to south, north to south, north to south, north to south, into the south, and out of the north. So that's our idea of nout and sin. Place a letter X where the magnetic field is strongest. So we can see that's where the highest flux density is. So more field lines, more magnetic field lines in the same area. So that must be X, and we know it's at the poles. It says describe two differences between the magnetic field and a uniform magnetic field. So we know a uniform magnetic field is if I've got my north to south, and we always show it, just do 3 lines. So this we can see that the spacing changes, but on this one the spacing is the same. That is its uniform. So that's a uniform magnetic field. This is not uniform because the spacing's changed. So describe two differences. The uniform magnetic field has straight lines. The above has curved lines. The uniform magnetic field has parallel lines. This doesn't. You can actually draw a picture to help you. The uniform magnetic field has the same strength throughout here. This one doesn't. We know it's stronger here than it is up here. So any two of those. Not particularly easy to get the wording right on that. State how a uniform magnetic field can be attained in a school laboratory. So we've done the one already. Get a pair of magnets in attraction. Or the other one is we will end up with, if we take a solenoid, we'll end up with a uniform magnetic field inside a solenoid. So any one of those two, but not outside the solenoid. Outside the solenoid, we'd end up with our butterfly, and our straight curve. So any one of those two answers. So place two opposite poles from bar magnets close to each other in attraction, or inside a solenoid. That word is important. Don't just say with a solenoid, it's inside the solenoid. Next one, we've got the Earth. So we know, we call this the North Pole. There's the South Pole. But actually, in terms of if we were to imagine a magnet, the North Pole of the Earth is actually the South Pole of a magnet. And that's because we call this the North Seeking Pole of a magnet. So a North Seeking Pole points north because it's actually attracted to a South Pole. And it says sketch the magnetic field outside and inside the Earth. So here we go. We're now going to go butterfly, stick into that there. Let's just do that again because that's rubbish. So butterfly, and if I wanted to, I could add some extra bits on the side. I'm making a right hash of this. Let's make it a little bit better. Let's make that a little bit better. Let's have that. If I wanted to, I could put 2 little ones here. We know that the magnetic field inside and outside the Earth, so now it goes out of the north and into the south, north to south, north to south. And what we can see is this South Pole is attracting to the North Pole of a magnet, but it's the actual geographic South Pole. So it says state which part of the Earth generates its magnetic field. So this is the outer core, which is the liquid metal in the outer core, because it's been spun around, so it induces a magnetic field. And then our last question on this is we've got our old favourite F equals BIL, and they usually give us unit changes. So calculate the magnetic flux density, so that's B. So we know that B equals F over I times L. Now let's look for unit changes. 0.6 meters long, happy with that. Millitesla, gonna have to divide that by 1,000 to get 0.0931. I think that works. If not, we'll see it down below. And the force of the wire is in newtons. So we're pretty happy with all of that. Shove it all together, and we've got an answer of 2 times 10 to the minus 4. They would have accepted that answer there, but you can see it's just worth, when it's 199 rounded up. And that's it.